new here, and I'm sorry about the early hours. I really should apologize for Physics 209, which is the previous course. Of course, you might think you should blame that on Martin instead of me, but since I do the course assignments, I'm the one that put him in the 8 o'clock slot, so it's really my fault. And I'm sorry about the 8 o'clock hour, but it really works out best for the scheduling of GSI assignments and things of that sort to do it at 8 a.m. Professors hate it as much as the students do, I think. All right, so this is the graduate course in quantum mechanics in the physics department, and my name is Robert Littlejohn. My office is 449 Bird, which I'll put down here also. I want to say, first of all, that if you received an email from me yesterday, it's because you were already enrolled in the course. And if you read that email, you'll know that it directs you to this website, which is the website for the course. If you did not receive an email from me yesterday, then please copy down that web address and go to that website. Make sure that you can access it. Do it right away because it's important to get organized. And read what's on the website because it contains the organizational and logistics information about the course, things like grading policy and stuff like that, which I'm not going to go over in the course, in lecture. That'll be important. That'll be the place where homework assignments will appear, all this stuff. You really need to know about that if you're going to take the course. Another thing is that I'm maintaining an email mailing list for the course in which I hope to have all of your email addresses on a big long list, which I use to send you information if there's some emergency or if I'm sick and can't come to lecture, or if there's an error in the homework and you need to know about it, I'll send it to you on that email mailing list. So if you're taking the course, especially for credit, if you're auditing, you can sign up for this email mailing list too. I don't care. But if you're taking the course, you certainly want to be on the email mailing list. Now again, if you received the email from me yesterday, you don't need to do it because you're already on it. But if you did not receive the email, then please send an email to this address, physics221@berkeley.edu, and just say, please put me on the email mailing list. You could also use that email address to ask me questions, but don't rely on it too much. I mean, don't think that an hour before the homework is due you can send me a question and you'll get an answer, because I don't necessarily answer that quick. It's better to make use of the office hours and the discussion sections for that purpose. So please make sure you're on the email mailing list. If you drop the course and don't care anymore about the course, send me an email to that address and say, remove me, and I'll take you off. All right, so that's all I want to say about organizational and logistics matters. This course is it's a two-semester course. The first semester, 221A, requires as a prerequisite a full year of undergraduate quantum mechanics. And if any of you have not had that, I ask you to, basically you don't have my permission to take the course unless you come see me to get that permission. So please do so if you haven't had a full year of undergraduate quantum mechanics. Also, if you're an undergraduate, I'd like you to come ask my permission. I just need to talk to you about things because you make sure you know what you're getting yourself in for. All right. One of the purposes of 221A is to go back over this full year of quantum mechanics that you've had already and to organize it in a more logical and consistent way, paying attention to fundamental principles that maybe you didn't have time for before. That's part of the purpose. Part of the purpose also will be to review the material. We'll also introduce some new material in this semester too. So as part of this program, I want to begin my first several lectures, in fact, on the mathematical methods or mathematical formalism of quantum mechanics. Most of this won't be all the mathematics we'll cover in the semester. Later on, we'll have to come back and do a little more, but this is most of it in this first week. And the mathematics mainly deals with vector spaces, in particular Hilbert spaces. Hilbert space is a particular kind of vector space, and you can read the official definition of a Hilbert space in math books. I won't go into that. Let me just say that Hilbert spaces are the spaces of wave functions, or let's say this, that the spaces of wave functions which occur in quantum physics actually are Hilbert spaces, and so we'll call them that. In any case, I want to begin with the mathematics of Hilbert spaces. Now, to get you oriented in this, I'm going to call on your experience with wave functions and things like that. I assume you know quite a bit already. So to begin with, and to get oriented, let's talk about wave functions in a one-dimensional problem. Let's see, I want to have the center board here. Is this the center board? Yeah, okay. So let's begin by talking about a wave function psi of x in a one-dimensional problem. And you know pretty much what this is. You know in particular that the square of the wave function is the probability density for making the measurements of position on the particle. Likewise, I hope you know that there's a momentum space wave function phi of p, and it can be given by what's essentially a Fourier transform of the position or configuration space wave function, as it's called at the top, e to the minus ipx over h bar psi of x. And this also has the square phi of p, absolute value squared, which represents physically the probability density in momentum space for making measurements of position, measurements of momentum. Now, so there's really two wave functions, psi of x and phi of p. And they're related to one another by invertible transformations. It's really a Fourier transform. Now, let's suppose in addition that we've got some energy eigenfunctions. Let's say we call them un of x is equal to en un of x for some problem. And let's suppose that they're discrete and non-degenerate eigenfunctions for simplicity. Then you know you can take an arbitrary wave function psi of x and write it as a linear combination with expansion coefficients I'll call Cn times the energy eigenfunctions. And you know that the expansion coefficients are given by an integral over x, which is un of x complex conjugated times psi of x. These are linear transformations that convert you back and forth between the psi and the coefficient c's. Well, these coefficient c's form a sequence. Let's call it c1, c2, dot, 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 like this. And this sequence of coefficients can be thought of as, quote-unquote, the wave function in energy space. Okay? Position space, momentum space, energy space. There are three different types of wave functions. Moreover, the square of these coefficients, Cn squared, I hope you know, this is interpreted as the probability of making a measurement. When you make a measurement of energy, it's the probability of getting the eigenvalue En, which is associated with that coefficient. So these are what we have here actually are, these can be thought of as three different wave functions which describe the same physical system, the same state of the physical system. And from a certain point of view, these are all equivalent descriptions. This is certainly true from the mathematical point of view, because everything that all the questions that one wants to ask in a physical sense about a quantum system, and it ultimately boils down to probabilities of making measurements, all of these calculations can be done in any one of these three wave functions, or as we say, representations, position, momentum, and energy representation of the wave function. And so from this strictly mathematical standpoint, there's no reason to think that any one of these wave functions is privileged or special over any of the others. Now, there's a psychological bias in thinking that the psi of x wave function is the privileged one, that it's better than the others somehow, or that it's a starting point. Why is this so? It's partly because we're used to thinking about wave functions in physical space, or functions, scalar fields, scalar and vector fields in physical space, electric fields, pressures, pressure of fluids, and things of that sort, things that we can measure in physical space. And so why isn't psi like that? Well, when Schrödinger was starting to write down the Schrödinger equation, that's how we thought of psi, as a physical field in physical space. However, it's pretty clear that that's actually an interpretation that doesn't hold up, because physical space is not the same as configuration space. Configuration space is basically X space. Why? Not in general, it's not. Why? Because you may have a wave function for two particles, in which case the wave function depends on the positions of both particles. So it's not a wave function on physical space, it's really a wave function on two copies of physical space. Configuration space, you see, is not the same as physical space. So that's one difference. Another difference is that if you get down to actually thinking about measuring a wave function psi of x, let's say for a single particle, let's go back to that, so you have just a single particle on physical space, think about measuring that. We'll talk about that later in the course. You'll find out the measurement process is really very different from the kind of measurements you would make of an electric field or a pressure in a fluid, where in principle you can just go to a point and measure it. measure the number. It's not so simple with psi. Certainly it's not hard to measure the square of psi. In principle, it's not hard, because it's a probability density, make repeated measurements and just count how many particles lie in a small interval. That gives you the probability. But finding the phase of the wave function is a different matter and is much more subtle. There's all kinds of subtleties that don't occur in the measurements of classical fields. So, for many reasons, it's best not to think of psi of x as being defined in physical space, but rather on this x space or configuration space. All right. Now, so with that background in mind, then, it's desirable in developing the formalism of quantum mechanics to use a notation which does not prejudice the choice amongst these observables. By the way, clearly these wave functions, clearly these observables are associated with, these wave functions, these three wave functions, are associated with three different observables. Position, momentum, energy in this case. And one can come up with other observables, angular momentum and anything else you want to measure, and each one of them has its own wave function. And these are all equivalent, give us equivalent descriptions of the same reality, the same quantum reality. So, in view of this democracy or covariance of quantum mechanics under changes of what we call representation, position, momentum, energy representation, and others, these covariance principles were worked out in the very early days of quantum mechanics by notably von Neumann, but others, Dirac, and so on. In view of this covariance amongst these different descriptions, it's desirable to have a notation for describing the states of systems that doesn't prejudice the choice. And so that's what the Dirac notation does, and that's what I want to tell you about now. So in the Dirac notation, we speak of kets, or also called ket vectors because they are vectors. And a ket is denoted by this kind of a notation, like this. And it's supposed to stand for any one of those wave functions up there. And it's customary to insert into a ket vector an identifying symbol, such as psi. I'll put a psi in there. It doesn't mean that it stands for psi of x. It really stands for all of those wave functions. But it's an identifying symbol of the ket. And a ket vector belongs to a vector space, which I'll denote by a script E like this. It's a complex vector space, which is called the Hilbert space. And as I say, I won't bother you with the official mathematical definition of a Hilbert space, although there is one. But rather just let's make the remark that Hilbert spaces are, in quantum mechanics, are the spaces of wave functions, and that'll be enough for us. That's how we'll use the terminology. Anyway, it's a ket vector in this space. Now then, just to say a few words about the physical postulates of quantum mechanics. We'll get into this in more detail in about a week. The physical postulates of quantum mechanics assert, in the formulation I'll present in this course, they assert that corresponding to every physical system, there is a vector space, in fact, a Hilbert's complex vector space, a Hilbert space, which is associated with a system. And it gives ways of knowing what the Hilbert space is based on the kind of measurements you can make on the system. We'll go into this in more detail later on, but in particular, there's physical principles that tell you what the dimensionality of the space should be. You'll find, for example, for spin systems, the space is finite dimensional, and for systems that include a position variable, it's infinite dimensional. In any case, Hilbert spaces may be infinite dimensional. To say that this is a complex vector space means that, mathematically speaking, you can form linear combinations of vectors with complex coefficients. That's what a complex vector space means. A real vector space means you're restricted to real coefficients when you make linear combinations. So in particular, it means that it's meaningful to talk about linear combinations of ket vectors like this, C1, psi1 plus C2, psi2. This is supposed to also belong to the Hilbert space E, where C1 and C2 are complex numbers. I'll write this by saying that it belongs to the complexes using this mathematical symbol for the complex numbers. All right. Now, crudely speaking, this is similar to the idea of linear superposition of electric fields in physical space. But remember, the wave function really isn't in physical space, so this is something else. But it is certainly linear superposition of vectors. Moreover, there's complex coefficients, and you might ask, why do we need complex numbers? Why can't we do it with just real numbers? We'll see later on when we study spin systems that it's impossible to do it. You can't satisfy the physical postulates of quantum mechanics with only real numbers. Okay. Now, people that study chemistry sometimes take courses in chemistry, they lose this because most of the problems in chemistry involve only real wave functions, so they have real coefficients. But actually, they have to be complex. All right. All right, so this is the beginnings of the Ket notation and the Ket vectors. By the way, the physical postulates that I'll speak about later on describe how the physical state of a system can be associated with a given Ket vector. I'll just say one thing about that now, however, which is that a physical state is actually not associated with a Ket vector, but rather it's associated with what you call a ray. It's associated with a ray in the Hilbert space E. What a ray is it's not just a single vector. If we take the origin of the vector space, call it O, and I draw a vector here like this is our vector, Ket vector psi. What the ray is it's a set of all vectors that can be obtained by multiplying psi by any complex number. You can think of it as being all the vectors that lie in a one-dimensional subspace where the magnitude is scaled, also the phase factors get scaled. A ray is a Ket vector it's a Ket vector, but it's a Ket vector. Let's put it this way: the state is a Ket vector modulo the overall normalization in phase, which don't have any physical significance. So the physical state is independent of normalization in phase. So in any case, the physical state corresponds to a whole ray, one-dimensional subspace of the vector space. All right, so that's a little bit about Ket vectors. Now, you're no doubt roughly familiar with the idea that Kets, like psi, are somehow supposed to correspond to wave functions psi of x. That's the idea. Before I go into that, I want to say that the program I'm trying to follow here is to start with the physical postulates of quantum mechanics, which lead to Ket vectors. We won't talk about wave functions. In effect, what I'm going to do is develop mathematics of Ket spaces and then later derive wave functions from the physical postulates. So I won't talk about wave functions at first, except for purposes of illustration, as I did up above, up here, because you know about wave functions already. But nevertheless, behind the scenes, we're thinking of Ket spaces as wave function spaces. And I'm sure you know that Kets are supposed to correspond somehow to wave functions. And I suppose you also know that bras that look like this are supposed to correspond to the complex conjugates of wave functions. Now, so I want to introduce the subject of bras now. The question here is how do we, if I don't talk about wave functions, how can I talk about a bra, which is supposed to be a complex conjugate? The answer is the following. As we say that a bra, or a bra vector, because a bra also is a member of a vector space. Just first of all is the notation. It's given in Dirac notation like this, with a kind of a reverse, it's a reverse of a Ket. And as in the case of a Ket, it's convenient to put in an identifying symbol for the bra, just to identify it or label it, distinguish it from other bras. And what is a Ket? What is a bra vector? A bra vector is a map. It's described this way. It's a linear map, as a matter of fact. It takes us from the Ket space over to the complex numbers. And what that means is that if I have a bra, which I call alpha like this, it's something that can act on Kets like this. And what does it produce? It produces a complex number. And you can write it like this way if you want, but we usually don't write it that way because it's too many parentheses. We usually just drop the parentheses and write it this way as alpha psi. So this is just the value of the linear map alpha acting on the Ket vector psi. All right. Now, and then I guess I did do this wrong because I'm supposed to do another point first. All right, let's do this way. Now, it's pretty easy to see that the bras as linear operators. Now, by the way, you're used to linear operators like Hamiltonian and the momentum and so on operators in quantum mechanics. Bras are not operators like that. Those usual operators like Hamiltonians in quantum mechanics are operators that act on the kets, and what they produce is another ket. They map kets into kets. A bra is a linear operator that maps kets into complex numbers. It's a complex valued linear operator. It's kind of a simpler linear operator, actually. Right. Bra vectors form their own vector space. If you take the set of all bras, like this, it forms its own vector space. It's easy to see how to multiply bras by scalars. You just multiply the answer by a scalar. And it's easy to see how to take linear combinations of bras. You just add up the answers for the different bras. I'll be explicit about this. C1 alpha 1 plus C2 alpha 2 is a linear combination of bras. And if we allow this to act on a ket, the answer is C1 alpha 1 psi plus C2 alpha 2 psi. And so this thing in the parentheses is another bra. So indeed they form a vector space. And the set of bras like this is sometimes called the dual space to the original ket space, and it's denoted I'll denote it this way with an E star on it, a star indicating it's a space of bras instead of a space of kets. You know, if you were doing wave functions, you would say, oh, well, isn't the complex conjugate wave function just a wave function, so it belongs to the same space as the original space of wave functions. That's a simple point of view. But in fact, it's more. It turns out that it's deeper and more convenient, ultimately, to regard this as a separate space, which we call the dual space. All right. Now, this still doesn't tell me. This still doesn't tell us what's the analog of the complex conjugation operation. How do we complex conjugate a ket? Well, you don't complex conjugate kets, but you do something similar, and it works like this. It relies on the fact that the ket spaces, that's to say Hilbert spaces, possess a scalar product, a way of taking scalar products of vectors. And this is related to the metric, which I'll tell you about now. The metric is a function which I'll call G, and what it does is it takes two copies of the ket space and maps it into the complex numbers. This is math notation. If you're not used to it, what it means simply is that G acts on two kets, which maybe I'll call psi and phi, and what it produces is a complex number. Like this. Acts on a pair of vectors. And this metric G is supposed to have certain properties, which I'll try to list here in case I don't run out of space. Properties of the first property is there's really two properties at first. One is that, call it 1A, is that G is linear in the second operand, which I'm calling phi here. So what that means is that if you let G act on psi comma phi, let's put it this way, linear combination, C1 phi 1 plus C2 phi 2, if we let it act on a linear combination in the second slot, replace that by linear combination, then you can spread it out just by linearity. So this becomes C1G acting on psi, comma phi 1, plus C2G acting on psi, comma phi 2, like this. That's the linearity. 1B is the second property, which is that it's antilinear in the first operand. And I'll tell you now what antilinear means. Is if I replace the first operand by a linear combination, I'll leave the second one alone, then we have G of, let's say, C1 psi 1 plus C2 psi 2, comma phi. What is that equal to? Well, it's equal to C1 complex conjugate times G acting on psi 1 comma phi plus C2 complex conjugate G acting on psi 2 comma phi, like that. The term antilinear, which we'll encounter once in a while in this course, means that when you apply something to a linear combination where you have expansion with complex numbers as coefficients, and when you expand it out, you have to take the complex conjugates of the coefficients. Anyway, G is linear in the second operand and antilinear in the first. So those are two properties of it. Let me try to see if I can put the other properties over here. There's a second property, which let's call a symmetry property of G. And the symmetry property says that if I take G of psi phi, a pair of kets, the answer is G of phi psi in the reverse order, which is a complex number, but I have to complex conjugate it. This is the symmetry property. And the third property is called the positive definite property. And it says this, is that if I take G and let it act on two kets which are identical, the same ket in both slots, well, first of all, before I write anything out, notice that by the property number 2, the answer has to be real, because it's equal to its own complex conjugate. So this is a real number. And in fact, it turns out it's always a positive, or it's a positive number or 0. This is for all psi, for all state psi in the Hilbert space. And it equals 0 if and only if the state psi is equal to 0. It vanishes the G value symmetrically. The G with the same vector inserted in both slots is equal to 0 if and only if the vector is 0. All right, so those are the three properties of the metric. The metric in a real vector space is a way of doing dot products of vectors, and in particular, the metric, you take the scalar product of a vector with itself, you get the square of the length. That's how it is in a real vector space with a Euclidean metric. It would satisfy the real analog of these three properties. So roughly speaking, this G of psi psi here, which is a positive number, is interpreted also in quantum mechanics as the length of the ket psi. Length, quote unquote. It's a geometrical analogy or metaphor for thinking about the geometry of these complex spaces. Now, so in effect, we're going to develop this ket formalism, and then later we'll derive wave functions from it. Not treating wave functions as the starting point. Yes, all right. Now, next I need to tell you about something which in doctorized book is called a dual correspondence. Actually, it's a fancy language for Hermitian conjugation, which you know about already, but I'll tell you how it works. The idea is this: let's consider the metric acting on two kets. This is, like I say, can be interpreted as a scalar product of the two kets. Let's consider this metric acting on two kets, and let's regard the first one as being fixed, and the second one as being variable. So then this can be regarded in effect as a function of just a single ket, the phi ket. And moreover, it's linear in the phi ket because that's the second operand, and it is a complex value. So this is a complex valued linear operator acting on kets phi, and so by our definition of a bra, it's actually a bra vector, or the bra acting on phi. So this is some bra acting on phi by the definition of a bra. And what is the bra? Well, the bra is a linear operator, but clearly it's a linear operator. It's associated with the psi here that we fixed. So what we do is we write this way. This is a definition now. We write this as a definition of psi phi. That is to say, this is the definition of bra psi. We started given a ket psi, and this associates it with a bra psi. So what this formula does is it defines a mapping that takes us from a ket psi This is called, what Sakurai calls this is a dual correspondence, and takes us over to a bra side. The definition of a dual correspondence is this formula. And in fact, after a while, we'll stop using the G notation. We'll end up just writing it this way. It means the same thing. All right. But instead of using DC, there's a more common notation, which is to use the dagger notation. That's to say the answer, which is the bra here, we'll say that this is the ket side with a dagger on it. The dagger is Hermitian conjugation, which is here being defined in its action on ket vectors. And what it does is it converts ket vectors into bra vectors, which are defined by the formula at the top. And this dual correspondence, if you like, you see, is a mapping that takes you from the ket space over to the dual space, the E star. Did I mention that before, that the dual space E star is the space of bras? So it maps you from kets to bras. If you're working on a space of finite dimensions, and you have these postulates of the metric G, it's easy to show that the dual correspondence is invertible. The dimension of the bra space is the same as that of the ket space. And moreover, every bra which is created in this, or every bra, in fact, is the image of some ket under this dagger operation. So the kets and the bras are placed into one-to-one correspondence. And therefore, it has an inverse, so that you can do a DC inverse that takes you from bras back to kets. And this inverse is traditionally denoted also by the same dagger notation. So what we get is we can say that if I have a ket side and there's a bra side, that I get by applying the inverse of the dual correspondence, I just use the same dagger notation for it. It isn't really the same operator, it's really the inverse of it, but it's, the notation doesn't cause me trouble because if you square it, you get the identity. You see, it's a consequence of this that if I take psi and dagger in twice, I just get psi back again. So in effect, we define the dagger notation now of both kets and bras, and it just amounts to switching one back and forth into the other. All right. The dual correspondence is antilinear. If I take a linear combination of kets, and I form the dagger of it, what I get is C1 star bra psi 1 plus C2 star bra psi 2. This follows just from the fact that the G operator is antilinear in the first operand. That's what makes it an antilinear operation, the dual correspondence. A consequence of this structure that I've developed so far is the Schwarz inequality, which I'll tell you about now. The Schwarz inequality is important in quantum mechanics because it leads to the Heisenberg uncertainty relations, as we'll see a little later. If you apply the Schwarz inequality on a real vector space, you'll find that it's equivalent to the statement that the shortest distance between 2 points is a straight line. And in some sense, even in complex vector spaces, you can think of that as being the geometrical meaning of the Schwarz inequality. But in any case, here's how it's stated. The Schwarz inequality says that if you take the scalar product of a phi with a psi, that's a complex number, and you take its absolute value squared, this is less than or equal to the scalar product of phi with itself times psi with itself. Both those numbers on the right-hand side are real and positive, so their product is real and positive, and the statement is that the scalar product is less than the product of the squares of the two vectors. We can think of psi as being the square of the vector psi, a real number, real and non-negative number. So I won't use the Schwarz inequality yet, but at least let me prove it. It works like this. Oh, and by the way, there's an addition to this too, which is that we get equals. Instead of an inequality, it turns into an equal sign if and only if the kets psi and phi are linearly dependent. So that's the Schwartz inequality. The proof, which I'll outline quickly, runs something like this, is let's define a ket alpha, which is equal to psi, plus a complex number lambda times the ket phi. We'll take a linear combination of the two kets, in other words. And we form the scalar product of alpha with itself, which, as you can see, is going to be psi scalar product with psi, plus lambda times psi scalar product with phi, plus lambda complex conjugated times phi scalar product with psi, plus the absolute value of lambda squared times phi scalar product with phi itself, like this. And because this is the scalar product of a ket with itself, the result has to be greater than or equal to 0 by postulate number 2. Or is it? I can't read it here. It's number 3, isn't it? Number 3, yes. And postulate number 3, this is greater than or equal to 0. Now, lambda is any complex number here, and it turns out, if you play with this for a while, that an interesting choice is to let lambda be equal to minus the scalar product of phi with psi divided by the scalar product of phi with itself. And I'll let you do the algebra. If you plug this in to these 4 terms here, what you find is that the last 3 terms are all equal except the middle 2 ones have got a minus sign on them, so it goes -1, -1, +1. And the result is this, is that alpha scalar product with alpha is equal to scalar product of psi with itself minus the absolute value of phi scalar product of psi squared divided by phi scalar product of phi. This is greater than or equal to 0. And just by multiplying through by this positive number here, you see you get the Schwartz inequality up above in the first form. There's a little extra work to do to show the second form, that you get an equal sign if and only if they're linearly dependent, and I'll let you refer to the notes to see how that works out. Okay. So that's a result that we put here because it's something we can derive at this point. Now, next, let me move on and say something about linear operators. And I don't know what to call this. How do I even access this backboard? How do you even do it? I don't get one or the other. That's the reason I can't use that third board. I thought you'd be supposed to be able to raise 2 of them at once, but apparently not. One goes down, the other comes up. Okay, well, I'll just have to alternate back and forth. Next, I want to say something about linear operators in quantum mechanics. Here I'm referring to the kinds of things like energy, momentum, and Hamiltonians, which you are familiar with. So a linear operator is a mapping that takes us from the ket space to itself, and it's supposed to be linear, so that it has the obvious distributive law over linear combinations of ket vectors. It's also possible to talk about antilinear operators where you need to take a complex conjugation, a complex conjugate of the coefficients when you have linear combinations. I'm not going to say much about antilinear operators now because most of the operators we deal with are linear. There's one important antilinear operator in quantum mechanics, which is time reversal, and we'll cover that later in the course. But don't worry about the antilinear operators when we get to them. And so for now, let's just talk about linear operators, which covers most of the cases. Hamiltonians, etc., are linear operators. Now, one of the things to say about linear operators, if you've got one, is that linear operator acts on kets. That's where they begin life. Can we also talk about linear operators acting on bras? Is this possible? I mean, if we do, it isn't really the same operator, but I'll call it that anyway. Can we define this? And the answer is yes. It works like this. So the idea is that if I have L acting on psi, that this is defined because L is a linear operator acting on kets. And what I'd like to do now is to say, what is this if I let the linear operator act on a bra? What's the meaning of that? Well, if the linear operator acts on a bra, it's supposed to produce another bra. So this thing, psi L, is a bra, and therefore it's a linear map that takes kets into complex numbers. And so therefore, I should be able to let this thing act on a ket phi, and I should get a complex number. And in fact, I can define this bra if I just say what the complex number is and verify that it's in fact linear. That's the things I need to do. Well, here's the simple answer. The complex number is going to be this. It's going to be the bra psi acting on the ket L phi. Because remember, we know what L does to kets. So this equation, in effect, becomes a definition of psi L. So I'll make this three little triple equal sign here because that means definition. Here, that means that here. So this is a definition of, this gives us a definition of psi acting of psi L, of L acting on psi from, as we say, it acts from the right onto a bra. We say here it acts from the left onto a ket. Now, one of the consequences of this definition is that parentheses don't matter. So it's customary to drop them and just to write this way as psi L phi. But lying behind this is the understanding that you can let L act either to the right or to the left, and it won't make any difference in the answer. So this is what you call a matrix element of the operator L, linear operator L. Tell you now about the outer product. Let's suppose we're given two kets which I'll call alpha and beta. You don't have to use Greek indices for kets, but Greek labels, but I'm doing that mostly here. Suppose I'm given two kets alpha and beta. Then I want to define a linear operator, which is called the outer product of alpha and beta, which is written this way as alpha beta. It looks like a ket juxtaposed with a bra. So this is a linear operator, supposed to be a linear operator. And it's called the outer product. Well, I already said that, so I won't say it again. It's called the outer product of kets alpha and beta. And how do we define it? Well, if it's a linear operator, it means we can let it act on any ket, and we should get another ket. And what will the answer be? It will be this. It will be ket alpha times the scalar product of beta with psi. In other words, you could say the definition of the outer product amounts to just reading these three symbols juxtaposed with a different ordering of parentheses. You do it like this, or you do it like this. On the right-hand side, you see this now becomes a complex number multiplying times a ket. On the left-hand side, it's an operator acting on psi. And this defines the operator. This is the definition of it. So that's the outer product. The outer product is essentially the same as what people call the tensor product or dyadic product. If you ever study tensor analysis, that's what they call it. Now I want to say a little bit about basis vectors. We know from linear algebra that a basis is a set of vectors that span the space. And that means that they're, they span the space and they're also linearly independent. A set of linearly independent vectors that span the space. So in a ket space, let's suppose for simplicity that we talk about a discrete basis. So we've got a set of ket vectors I'll call n, where n is indexed by 1, 2, 3, something like this. And the number of such vectors is the dimensionality of the space, which could be infinite, because ket spaces are oftentimes infinite dimensional. The basis may or may not be orthonormal. Bases don't have to be orthonormal. Usually, but not always, in quantum mechanics we use orthonormal bases. So we say the basis is orthonormal, as I'm sure you know, if the scalar product of a pair of basis vectors is prime or delta like this. They're the most useful bases in quantum mechanics, so let's talk about those orthonormal bases. Then, if I have an arbitrary ket, or as we say, state psi, because this is a basis, that means I can expand this as a linear combination with some coefficients of the basis cats. And by the orthonormality relation, it follows immediately that its expansion coefficients are just given by the scalar product of the basis cats with the original vector psi, like this. I'm sure you're familiar with this sort of thing. Now in this expansion, I've got a complex number multiplied times a cat. When we write that, we can also put the complex number on the other side. It doesn't matter which side you put the complex number on when you multiply a complex number times a cat. But I'll put it over here on the other side, because now what I want to do is take the expansion coefficient and plug it in here. And if you do that, then you get the sum on n of n cat n bra psi like this. So read one way, this is cat n times a complex number. But we can read it another way, which is outer product of n acting on cat psi, like this. In fact, let me move the parentheses like this, because psi itself doesn't depend on n. And so what you see is that there's an operator which is in these parentheses here, and when it acts on an arbitrary cat, it reproduces the same cat all over again. And therefore, that operator must be the identity. And so we say, we write it this way, is that the sum of the outer product of the basis cats with themselves is equal to 1, where 1 stands for the identity operator. It's common in quantum mechanics to write the identity operator as just 1. And this is called resolution of the identity, which is associated with the basis, here assumed to be a discrete basis. Later on, we'll generalize this to the case of continuous bases, but this is what it looks like. So this is an example of where the outer product appears, is in a resolution of the identity. All right. Now, another topic. I previously defined the dagger operation on cats, which maps them into bras, and the dagger operation on bras, which maps them into cats. Dagger operation is permission conjugation. It's convenient to extend the definition of the dagger operation to complex numbers, in which case it's just interpreted as same thing as complex conjugation. Now I want to extend this even further to define the Hermitian conjugate of an operator. Here's the idea. If I have a linear operator A, this is a linear mapping of the ket space into itself, I want to define the Hermitian conjugate of A, which will be another linear operator on the same ket space. And the question is how to define this. And the answer is the following, is that we say A dagger acting on psi is equal to, we first take the ket psi, convert it into a bra using the dual correspondence. You then let the operator A act on that. We know how linear operators act on bras, and then we take the whole thing and Hermitian conjugate it again. This is the definition of A dagger. Now, the question that arises is that if A is linear, is A dagger also linear? And the answer is yes, because you see, when I first take psi and then I convert it into a bra by the dual correspondence, that's actually any linear operation. And then I'm going to let A act on the bra. But then I Hermitian conjugate a second time, which is another antilinear operation. And so the result turns into a linear operator. So A dagger is linear, linear operator. All right, so this is the definition of A dagger. All right. Now, there's a whole bunch of simple consequences of this definition, which I'll just list out here. Let's see. So one of them is that if I take A and dagger it twice, I get A back all over again. That certainly applies in these other instances of the Hermitian conjugate operation. Another property is that if you take the product of two operators and you dagger them, you get the daggered operators in the reverse order. You have to reverse it. The third property is that if I take a matrix element of an operator A between two states psi and phi, this is equal to, well, perhaps I'll write it this way. Let's take the complex conjugate of that matrix element. This is equal to the original matrix element, but read in the reverse order where everything is daggered as you move through it. So we start on the right, at cat phi, we dagger it, turn it into a bra. The operator A gets turned into A dagger, and cat psi gets turned into, bra psi gets turned into cat. Just reverse the order of this. Here's another consequence of it. If I take the outer product of two cats alpha and beta and I dagger that, this is a linear operator, so I'll dagger it. What this turns into is the outer product of the two cats in the reverse order. These are all easy consequences of the definition. Now, one result of these definitions is a general rule in quantum mechanics whenever you're dealing with cats, draws, linear operators, complex numbers, all multiplied together. The kind of multiplication can be ordinary multiplication. It can be operators acting either to the right or the left, or it can be the tensor product of two cats. All it has to be is just some meaningful expression. The rule is that if you want to take the Hermitian conjugate of that, you read the expression backwards and you apply dagger to each item separately. Complex numbers go into their complex conjugate and so on. And in fact, there's a couple of examples of that rule right here. You see this has been read backwards. This star is the complex conjugation for the whole result, which is the complex number, the matrix element. Here you're reading it backwards and daggering things, reading it backwards and daggering. The rule applies quite generally. This is all part of the neatness or the advantage of the Dirac notation for calculations in quantum mechanics, is that it makes all these operations quite natural in the notation. All right. Now, as I'm sure you know, to make another definition, I'm sure you know that a Hermitian operator A is one which is equal to its own Hermitian conjugate. Definition of a Hermitian operator. Hermitian operators are related to operators what are called self-adjoint operators. If you're a mathematician, you go to great troubles to draw the distinction between these and to be aware of when one is the same and the other was, and when the two are the same and when they aren't. But for practical applications in quantum mechanics, we can consider self-adjoint and Hermitian as being essentially synonymous. If this worries you about it, you need to go study a course on functional analysis. I'll just put it that way. Actually, in finite dimensions, in a finite dimensional space, the two terms Hermitian and self-adjoint are equivalent. The only issue arises in infinite dimensional spaces, and I don't really want to get into the mathematics of technicalities of infinite dimensional spaces very much in this course. But in any case, for most practical purposes, we can regard these two terms as synonymous. All right. Now, if you have Hermitian operators, of course, I'm sure you know this, are particularly important because they represent physical observables. We'll gradually say more about why this is true as we go on. But right now, let me just say, I was going to say one more thing here. Yeah, let me just say one more thing here. Is that we say that a Hermitian operator is positive definite. Let me write this out. A Hermitian operator is said to be positive definite if you have this following property, is that if you form the matrix element of your operator A with the same state on both sides, that the answer is always non-negative. And furthermore, if you get equals to 0 if and only if the state psi vanishes. This is a definition of positive definite. A positive definite operator, from another point of view, is an operator whose eigenvalues are all positive. One can also speak of a non-negative definite operator, and that's one whose eigenvalues may include zeros, but they don't include any negative numbers. I haven't said anything about eigenvalues yet, but I will. I guess in the next lecture, we'll talk about the eigenvalues, the spectrum of operators and things of that sort. Okay, that's all for today. Is that the spaces of wave functions which occur in quantum space actually are Hilbert spaces, and so we'll call them that. In any case, I want to begin with the mathematics of Hilbert spaces. Now, to get you oriented in this, I'm going to call on your experience with wave functions and things like that. I assume you know quite a bit already. So to begin with, and to get oriented, let's talk about wave functions in a one-dimensional problem. Let's see, I want to have the center board. Is this the center board? Yeah, okay. So let's begin by talking about a wave function psi of x in a one-dimensional problem. And you know pretty much what this is. You know in particular that the square of the wave function is the probability density for making the measurements of position on the particle. Likewise, I hope you know that there's a momentum space wave function phi of p, and it can be given by what's essentially a Fourier transform of the position or configuration space wave function, as it's called at the top, e to the minus ipx over h bar psi of x. And this also has the square phi of p, absolute value squared, which are new here. And I'm sorry about the early hours. I really should apologize for Physics 209, which is the previous course. Of course, you might think you should blame that on Martin instead of me, but since I do the course assignments, I'm the one that put him in the 8 o'clock slot, so it's really my fault. And I'm sorry about the 8 o'clock hour, but it really works out best for the scheduling of GSI assignments and things of that sort to do it at 8 a.m. Professors hate it as much as the students do, I think. All right, so this is the graduate course in quantum mechanics in the physics department, and my name is Robert Littlejohn. My office is 449 Bird, which I'll put down here also. I want to say, first of all, that if you received an email from me yesterday, it's because you were already enrolled in the course. And if you read that email, you'll know that it directs you to this website, which is the website for the course. If you did not receive an email from me yesterday, then please copy down that web address and go to that website. Make sure that you can access it. Do it right away because it's important to get organized. And read what's on the website because it contains the organizational and logistics information about the course, things like grading policy and stuff like that, which I'm not going to go over in the course. In lecture. That'll be important. That'll be the place where homework assignments will appear, all this stuff. You really need to know about that if you're going to take the course. Another thing is that I'm maintaining an email mailing list for the course in which I hope to have all of your email addresses on a big long list, which I use to send you information if there's some emergency or if I'm sick and can't come to lecture, or if there's an error in the homework and you need to know about it, I'll send it to you on that email mailing list. So if you're taking the course, especially for credit, if you're auditing, you can sign up for this email mailing list too. I don't care. But if you're taking the course, you certainly want to be on the email mailing list. Now again, if you received the email from me yesterday, you don't need to do it because you're already on it. But if you did not receive the email, then please send an email to this address, physics221@berkeley.edu. And I just need to talk to you about things because you make sure you know what you're getting yourself in for. All right. One of the purposes of 221A is to go back over this full year of quantum mechanics that you've had already and to organize it in a more logical and consistent way, paying attention to fundamental principles that maybe you didn't have time for before. That's part of the purpose. Part of the purpose also will be to review the material We'll also introduce some new material in this semester too. So as part of this program, I want to begin my first lecture with the first several lectures, in fact, on the mathematical methods or mathematical formalism of quantum mechanics. Most of this won't be all the mathematics we'll cover in the semester. Later on, we'll have to come back and do a little more, but this is most of it in this first week. And the mathematics mainly deals with vector spaces, in particular Hilbert spaces. Hilbert space is a particular kind of vector space, and you can read the official definition of a Hilbert space in math books. I won't go into that. Let me just say that Hilbert spaces are the spaces of wave functions, or let's say, and just say, please put me on the email mailing list. You could also use that email address to ask me questions, but don't rely on it too much. I mean, don't think that an hour before the homework is due you can send me a question and you'll get an answer, because I don't necessarily answer that quick. It's better to make use of the office hours and the discussion sections for that purpose. So please make sure you're on the email mailing list. If you drop the course and don't care anymore about the course, send me an email to that address and say, remove me, and I'll take you off. All right, so that's all I want to say about organizational and logistics matters. This course is it's a two-semester course. The first semester, 221A, requires as a prerequisite a full year of undergraduate quantum mechanics. And if any of you have not had that, I ask you to, basically you don't have my permission to take the course unless you come see me to get that permission. So please do so if you haven't had a full year of undergraduate quantum mechanics. Also, if you're an undergraduate, I'd like you to come ask my permission.